There's two formulas for pressure. There's one that's a normal force, and there's a special one just for fluids. The first formula says pressure is force divided by area. That's the normal, and it applies to both solids and fluids. The second formula says rho GH, and this is only true for fluids, not for solids. This formula actually is more useful, easier to use, and applies to fluids. And in AP Physics, we have a whole chapter on fluids, so we're going to be using this equation more than the first one. Let's think of a simple example. Here is a tank of water. Let's place a block in the tank of water. We like blocks in physics. They are helpful for thinking. So the height in our equation, rho GH, is going to be from the surface of the water to the top of the block. So it's not the height to the bottom of the block or the middle of the block, to the top of the block. And what we do is we imagine that the water above the block is pressing down on the top of the block. This water above the block is creating pressure. Again, not all the water is above the block. Some's over here, and that's pressing down there, and it's not pressing down on the block. But the water that is above the block, that water is pressing down. So let's say this block is 1.5 meters. That height to the top of the block is 1.5 meters. We can calculate the pressure. The formula is rho GH. The density of water is 1,000 kilograms per meter cubed. Let's put those numbers in. This is going to be 14,700 pascals. We often write this in kilopascals. We divide it by 1,000. So 14.7 kilopascals. Okay, so that's using the rho GH formula, and we're going to be using that quite a lot. The best way to get an A on a test in physics is to do a practice test. On my website, there's a free practice test for fluids. If you click the link below, you can get the free practice test. We'll even mark it for you and let you know how you did. I'm going to try and derive this formula, the particular one about fluids, from the first one. Actually, this is kind of like an application of the first one, and we can quite quickly show that this one comes out of that one with a simple thought experiment. So we got to think in 3D here. Let's imagine a tank of water here. So this is just a big tank of water, and we place inside this tank of water a square box. So there's a square box there inside a tank of water. So this square box has a surface area on the top, surface area A. Now what we do is imagine a column of water above the top of that block. I don't know if you can see it. There's this column of water. I put it in green to be a bit different there. This column will also have a surface area on the top of A. It matches exactly the surface area of the block there. So this column is all the water that's directly above the block on the bottom. So any water not in that column is not above the block, and all the water above that block is that green column. So the force created by that column of water is the force creating the pressure on that area. So what's the force of gravity? What's the weight of that green column of water? So the force of gravity is just mass times gravity, and we're going to get mass from the density formula. Mass is rho times V. Now what's the V? We have an area, and we also have a height. That's going to be a height of that column. So the volume is just A times H. Pressure, we can now say, is force divided by area. And if we take our variables, we're going to get the force is rho AH times G. And the magic of this is the areas cancel out. So I get that the pressure that this column applies on the block is rho HG. And that's exactly what we had there. So these kind of derivations help us think about the equations in an abstract way and really understand what they're saying. So this is an application of that. And one of the key ideas that comes from this is that the area of the box in the water doesn't matter for the amount of pressure coming down on it. If there's a small block, there's a small green column. If there's a large block, there's a large green column. And it works out perfectly so the area doesn't matter. What does matter is the height of this green column, because that is saying how much water is above. So if there's something under a lot of water, there's going to be a high amount of pressure. If there's something under a little bit of water, there's only going to be a little bit of pressure. So let's think about one more example using the same kind of column thinking. Now this example might be a bit weird for you, but we're under pressure all the time. And I'm not thinking about the Queen song or your homework from physics. I'm thinking about the pressure that the air in our atmosphere is always there pressing down on us. Let's imagine there's a person just standing there on the surface of the earth. Above that person's head is air. Now, air is a gas which is a fluid, and it does have mass. So there is a force of gravity of that air pushing down. I want you to imagine a column going upwards. Now, air doesn't weigh very much, but it does have some mass, actually. And this column is very big. This is all the air above your head going all the way up to space. It's miles high. And because of that, it has some actually real mass. And you should imagine all the air in this column is like a hat or something that sits on top of your head, pressing downwards. And it turns out we can measure the pressure this air applies. So the pressure of air on your head is about 101,000 pascals. Remember that last thing with the water was only 14,000 pascals. This is actually a real amount of pressure. We often change this to 101 kilopascals, and it's also sometimes called 1 atmosphere of pressure. This is one of those numbers that's actually on your formula sheet given to you in the AP Physics equation formula sheet. I'll just make a few comments about this idea. Firstly, it's a bit weird to think about this. Air is creating pressure on you all the time. We don't feel it or experience it. We might think about that in the next video, but it's there and it's real. Secondly, it's not exactly 101 kilopascals everywhere. If you go up a mountain higher, there'll be less air and this number will be smaller. Maybe you could go somewhere deeper like under a mine and maybe this number will be a bit larger. But in questions in AP Physics, we usually take this number, 101 kilopascals, to be the density due to air above a person. I wonder if you've ever experienced the pressure of fluids in your life. Have you ever been scuba diving perhaps and had pressure of water above you? Write in the comments below if you've ever experienced the pressure of fluids in some way.